Welcome to Bright Minds Academy Goa. These classes are going to be for Goa Board Class 12 Mathematics. Today we are continuing with Chapter 1 Relations and Functions. So I'll be starting with the exercise 1.1. We are dealing with the first question here, which states determine whether each of the following relations are reflexive, symmetric and transitive. So we simply have to check whether the relations are reflexive, symmetric and transitive. So starting with the first question right here, we are given a set A. So I'm going to quickly write down the set A that is mentioned here. Set A is basically the set 1, 2, 3, 4 all the way up till 13 and 14. Now whenever you're given a finite set, it is important or it is necessary that you write down what the relation will look like. So if you see the relation satisfy the condition, it's an ordered paired x comma y such that 3x minus y will be equal to 0. So I'm going to take this equation right here and I'm going to find y from here. If I take y on the other side, I'll get y is equal to 3x. So we'll take different values of x and we'll find the corresponding values for y right here. So if I take the value of x is equal to 1 first, then y will be 3 into x, which will become 3 into 1, which is 3. If I take x is equal to 2, y would be 3 2s are 6. Then if x is equal to 3, y will be equal to 3 3s are 9. If x is equal to 4, y would be 3 4s are 12. Now if I take x is equal to 5, y would be 3 into 5, which is equal to 15. Now the problem right here is, if you look at this relation, if you look at this set A, 15 does not belong to the set A, so we can't take this particular element. So this is how my set will look like. So this is my relation right here. Now up front, if you see here, 1 comma 1 do not belong to the relation, therefore you can say that R is not reflexive. Next, for symmetric, we can just take randomly any element. We have 1 comma 3 which belongs to R, but we have here that 3 comma 1 does not belong to R, therefore you can say that R is not symmetric. Now for transitivity, what you have to do is you have to use the first element in such a way that this element right here, this ending element, has to be the starting element of the other set. So if you see such type of an element, we have is 1 comma 3 and we have 3 comma 9, because if you see this 1 comma 3 ends with 3, 3 comma 9 begins with 3. So I'll take that as my option right here. So I'll say that 1 comma 3 belongs to the relation R and 3 comma 9 also belongs to the relation R, but what do we have? The remaining elements of 1 comma 9 does not belong to the relation R, therefore R is not transitive. So hence we have proved that therefore R is neither reflexive nor symmetric nor transitive. Now the next question that we have here is the relation R in set N. Here the set N is a set of natural numbers and is defined by the equation R is the ordered paired x comma y such that y is equal to x plus 5. Now if you see right here, the condition is given that x cannot exceed 4. So what are the values that x can take? X can either be 1, x can be 2 or x can be 3. Now what are the corresponding values that y takes? Y, if you see, the relation is x plus 5, so for x is equal to 1, y is going to be 1 plus 5, which is 6. For x is equal to 2, y is going to be 2 plus 5, which is 7. For x is equal to 3, y is equal to 3 plus 5, which is going to be 8. So the ordered pair right here in the relation R are 1 comma 6, we have 2 comma 7 and we have 3 comma 8. Now that we have written what the relation looks like directly, if you can see from here, I can just take the random element 1 comma 1 do not belong to relation R, therefore R is not reflexive. Next we have 1 comma 6 belongs to R, but 6 comma 1 do not belong to R, therefore R is not symmetric. Now the next thing is very important. If you see right here, in order to prove or disprove transitivity, what is important is there has to be an element a comma b belonging to R, and there has to be an element b comma c belonging to R. Now this is the primary important things that have to be present in R for you to prove or disprove transitivity. But if you see, such two elements are not there in R, because if you see 1 comma 6 belongs to R, but there is no element that is starting with 6. There is no such element. At the same time, if you take 2 comma 7 belongs to R, there is no such element that starts with 7. At the same time, if you take 3 comma 8 belonging to R, there is no such element that is starting with 8. So what you can see from here is, since we cannot disprove transitivity, since transitivity cannot be disproven, hence the relation R is transitive. Now why? Because for a comma b belonging to the relation, there is no ordered pair b comma c belonging to R. So this is that is happening because a comma b is there, but there is no such element as b comma c belonging to R, so you cannot disprove. Now hence we'll write down the final statement. Therefore R is not reflexive, not symmetric, but is transitive. So we'll go to the next question right here. We are given that the relation R in set A, such as R given by ordered pair x comma y is divisible by x. Now first we'll understand what do you mean by y is divisible by x. So if I write an ordered pair here 1 comma, or I'll take a different example. So if I take an ordered pair here, for example 3 comma 6, this element is x element, this is our y. Now so what do we mean here is the second element right here, that is y or 6, is divisible by 3. Now what does this mean? That when you divide 6 by 3, you're gonna get a natural number, okay, or you're gonna get a positive integer. That is what I mean when I say 6 is divisible by 3. So in such a case, this will belong to the relation R. Now if I take the opposite way around, if I take 6 comma 3, this means that 3 should be divisible by 6, but we know that this is false, because when you divide 3 by 6 you get a fraction, therefore it is not actually divisible. Now that you know what y divisible by x means, we'll carry on further and we'll write what the relation R looks like. So if you take a relation, the set A, which is basically 1 2 3 4 5 and 6, we have relation R. Now my first question is, will 1 comma 1 belong to the relation? Yes, because 1 is divisible by 1. In such a way you can write 2 comma 2, we can write 3 comma 3 here, we can write 4 comma 4, 5 comma 5, and we can write 6 comma 6, because all of them are divisible by itself. Now the next thing, so if you write down the next number, which is, let's just say if you take 1 comma 2, definitely 1 comma 2 will belong to the relation, because 2 is divisible by 1. In the same way 3 is also divisible by 1, 4 is also divisible by 1, 5 2 is divisible by 1, and even 6 is divisible by 1. Next, if you take 2, then which are the numbers that are divisible by 2? 4 is divisible by 2, and even 6 is divisible by 2. If you take 3, only 6 is divisible by 3. There is nothing that is divisible by 4, nor by 5, nor by 6. So this is how your relation will look like. Now that we can say here is, for all A belonging to the set A, what will happen? A comma A will belong to the relation R. Why will A comma A belong to the relation R? Because if you use this condition right here, because A is divisible by itself. Next we have to check for symmetric. Now for symmetric, what does symmetric means? That if A comma B belongs to the relation R, then it implies that B comma A should also belong to the relation R. Now the trouble here is, if you take this to be true, then this means that B is divisible by A. For example, we can take 1 comma 6 belonging to R. Now but the problem here is the ulta will not always be true, because if you see here 6 comma 1 do not belong to R, because 1 is not divisible by 6. Therefore you say that R is not symmetric. Remember one thing, when you have to prove that something is not reflexive, not symmetric or not transitive, one example in such a case is enough. But if you have to prove that something is reflexive, like right here we can say that R is reflexive, here we have to prove it in general, like how I have proved here that a number is divisible by itself. Therefore for all A belonging to A comma A will always belong to R. In such a case, when you have to prove it reflexive, have to prove it symmetric, have to prove it as transitive, you have to show it in general. When you have to show that it is not, you can show using any one example. Now going next over to transitive behavior, what we'll do is we'll quickly see what will happen if you take a quick example. This is something that you can do in exam if you're not 100% sure of your answer. So you can take any one example. For example, we know that 1 comma 6 belongs to the relation R. Now the second element that you have to choose has to be in such a way that if this is 6, the first element here is also supposed to be 6. Now which is the other element in the set? If you see, if you take 1 as 1 comma 6, the other you have to choose as 6 comma 6, because it is starting with 6. So like that way, if you choose the other element as 6 comma 6, this also belongs to the R. Now what are the remaining elements? The remaining elements are 1 and 6. This also belongs to the relation R. But as I told you, since you have to, whenever you have to prove that it is transitive, you have to prove it in general. Now how will you prove such a thing in general? We'll quickly see this. We'll see for A, B and C belonging to the set A. We'll assume that if A comma B belongs to the relation R, and we'll assume that B comma C also belongs to the relation R. Now what does this thing mean right here? According to the definition, this means that the second number, which is B, is divisible by the first number, that is A. Similarly, we can say right here that the second number, which is C, is divisible by B, the first number, that is B. Now when I say B divided by A, B is divisible by A, that means B is divided by A, that means this will end up giving you a natural number or a positive integer. Similarly, if you apply the same logic right here, C divided by B should also give you a natural number, which is M. Okay, now coming back to what do you actually have to prove. Now I'll just write it down here. You have to prove that A comma C also belongs to R for it to be transitive. Now what does this mean according to the definition? According to the definition, this means that C is divisible by A, or this implies that C divided by A should be some natural number. Okay, so what do we have to focus on? We have to focus somehow on C divided by A. So what I'll do is I'll find the value of B right here. B is equal to A into N, and this I'll substitute right here. So from here I'll end up getting C upon, instead of B I'll substitute AN. So if I substitute AN, this will give you M. Now what do we need? We need C by A. So this N I'll take on top. So C by A would be equal to N into m. Again, n is a natural number, m is also a natural number, so in total that will give you another natural number, which is k. Since c divided by a is a natural number k, this implies that c is divisible by a, and this implies that a by c belongs to the relation R. Therefore R is transitive, and hence we have proven we'll come to the thing. We have showed that R is reflexive, we have showed that R is not symmetric, and we have showed that R is transitive. So we'll write a final statement. Therefore R is reflexive and transitive, but not symmetric. Now going on to the next thing right here, what we have is we have a relation R in the set Z. Now the set Z is the set of all integers such that it is defined by relation R ordered paired x comma y such that x minus y is an integer. Now if you see right here, this is for all the set of the entire integers, so we're gonna prove everything in general right here. Okay, now the first thing that we have to check is for reflexive behavior. Now so I'll just assume for a belonging to the set Z, I'll just find what is a minus a. Now why am I doing a minus a? Because I have to somehow prove that a comma a belongs to the relation R. Now what does a comma a belong to the relation R? According to the definition right here, it is the first value minus the second value, which is simply a minus a. Now we know this is equal to 0. Is 0 an integer? Yes, it's an integer. It belongs to the set of integers Z. Therefore a comma a belongs to the relation R. Therefore R is reflexive. Now the next thing that we have to check is for symmetric behavior. Now for symmetric, I'm gonna say for a comma b belonging to the set Z, I'm gonna assume if a comma b belongs to the relation R. Now since we have assumed that a comma b belongs to the relation, since we have assumed that a comma b belong to the relation R, what does this mean according to the definition? According to the definition right here, it means that a minus b is an integer. So I'm just going to take it equal to n, where n is an integer. Now I have to prove that b comma a also belongs to R, right? Now what does this mean according to definition? B minus a should be an integer. So from this thing right here, we'll quickly calculate what is b minus a. To calculate b minus a, I'll take negative signs on both sides. So I'll just change signs all throughout. So that will give me minus a plus b equal to minus n. So I'll just rearrange this part right here, which will give you b minus a equal to minus n. Now since n is an integer, minus n is also an integer, so this is equal to an integer. Therefore b comma a belongs to the relation R. Therefore R is symmetric. Now the last thing that I have to prove is the transitive behavior. Now for transitivity, I'll say for a comma b comma c belonging to the set of integers Z, we have if a comma b belongs to the relation R and b comma c also belongs to the relation R. Now what does this means? This means that b minus a is an integer n and c minus b is also an integer m. Then I'll say where n and m are integers. Now so the next thing that we have is, what do I have to prove? I have to prove that a comma c also belongs to the relation R. That means I have to prove that c minus a is an integer. This is what we are interested in. We are interested in C and minus C. Now if you look right here of what we have, I already have C right here and I already have A, so I'm gonna add the two equations. So this is equation 1, let's say, and this is equation 2. So I'm adding equations 1 and 2. I'll get B minus A plus C minus B equal to N plus M. So I'm adding the left hand side separately and then I'm adding the right hand side separately. So if you look right here, B minus B cancels, and if you rearrange it, I'm going to get C minus A equal to N plus M, which can write as another integer Z, where K belongs to Z, and therefore A comma C belongs to the relation R, therefore R is transitive. Hence we have proved that hence R is reflexive, symmetric and transitive. Therefore you can also say that R is an equivalence relation. This is the next question that we have right here. The relation R in the set A of human beings in a town at a particular time is given by. So the set A that we are interested in here is given to be set of human beings in a town. The relation R that is defined here is the ordered paired x comma y such that x and y both work at the same place. Now we'll quickly check for reflexivity. We'll say for x belonging to the set A. Now tell me one thing, will x comma x belong to the relation R? Definitely yes, because what's the condition for it to belong to relation R? That is x comma y, both of them have to work at the same place. So doesn't x and x, doesn't the person n itself work at the same place? Definitely yes, because a person works at the same place as herself slash himself. Okay, next we'll check for, therefore we'll say here that R is reflexive. Next we'll check for symmetric behavior. Now we'll say for x comma y belonging to the set A, we have if x comma y belong to the relation R. Now what does this means? This implies that x and y work at the same place. You can say it opposite as well, that y and x also work at the same place. And hence you can say that therefore y comma x also belongs to the relation R, therefore R is symmetric. Last we'll check for transitive behavior. We'll say for x comma y comma z belong to the set A, if x comma y belong to the relation R, then what does this imply? This implies that x and y work at the same place. Now, and we can also consider that y comma z belongs to R. This implies that y and z works at the same place. X and y work at the same place. Y and z also works at the same place. X and z work at the same place. And therefore you can say that x comma z also belongs to the relation R, and therefore R is transitive. Hence we'll write a final statement. We'll say that therefore R is reflexive, symmetric and transitive. So in total you can also account for the fact that R is an equivalence relation. This is the next question that we have here. X comma y such that x and y live in the same locality. It can be solved in the same way, the same set. So here R will again be reflexive, symmetric and transitive. Now this is the next question that we have right here. R is x comma y such that x is exactly 7 centimeters taller than y. So we'll first take the first case. First we'll check for reflexive behavior. Now we'll say for x belonging to the set A. Now definitely x comma x will not belong to the relation R, because a person is never taller than itself, because a person cannot be 7 centimeters taller than himself or herself. Now next we'll check for symmetric behavior. Now we'll say for x comma y belonging to the set A, let x comma y belong to the relation R. What does this mean? This implies that x is 7 centimeters taller than, I'll just draw a reference figure here. Let's say this is x and this is y. Clearly x is 7 centimeter taller than y. Now but is y taller than x? No. So y is not 7 centimeters taller than x. This implies that y comma x do not belong to the relation R, therefore R is not symmetric. Okay, next we have to check for transitive behavior. For here we'll say for x comma y comma z belonging to the set A. Now let x comma y belong to the relation R. What does this implies? This implies that x is 7 centimeter taller than y, and we'll say that let y comma z belongs to this relation R, therefore y is 7 centimeters taller than z. Now what does this mean? This is x right here, this is y right here. So clearly you can see that the difference between x and y is 7 centimeters. Now this is z right here, again the difference between this two is 7. So if you consider x and if you consider y, if you consider z, the difference between them is going to be in total of 14 centimeters. So you can say for here, therefore x is not 7 centimeters taller than z, therefore x comma z do not belong to the relation R, therefore R is not transitive, and therefore you can say that R is neither reflexive nor symmetric nor transitive. This is the next question that we have. R x comma y such that x is the wife of y. Now definitely a person cannot be the wife of itself, so for x belonging to the set A, x comma x do not belong to the relation R, because a person cannot be herself's wife. So therefore R is not reflexive. Okay. The next thing that we have to prove for symmetric. So we'll say for x comma y belonging to the set A, we say x comma y belongs to the relation R. Now this implies that x is the wife of y. Now definitely if x is the wife, this is X, this is Y, this is the wife, so definitely this is going to be the husband. So definitely this implies that Y is not the wife of X. This implies that Y comma X do not belong to the relation R, therefore R is not symmetric. Next we have to check for transitive behavior. Now here you have to always be very careful. Now we'll say for X comma Y comma Z belonging to the set A, we'll say if X comma Y belong to the relation R. This implies that X is the wife of Y. This is the case that you're gonna get right here. That is, X is going to be the wife, Y is going to be the husband. That is, Y is going to be a man according to normal societal standards. But here, will Y comma Z belong to the relation R? Because if Y comma Z belongs to the relation R, then Y is the wife of Z. Now this means that Y is the wife, so she is going to be a woman. But earlier we have just said that Y is going to be a man. So in that case, such type of an ordered pair will never belong to the set R or the relation R. Therefore we'll say that here it is, you cannot disprove that it is not transitive, so it is going to be transitive. Okay, so we'll say that for Y comma X, X comma Y belonging to the relation R, there isn't any ordered pair Y comma Z belonging to this relation R, therefore transitivity cannot be disproved, hence R is transitive. Okay, therefore R is reflexive, comma symmetric. R is not reflexive, not symmetric, but is transitive. We'll go on to the last question for this part of the question number 1. Here you are given that there is a relation X comma Y such that X is the father of Y. Now we'll quickly check for reflexivity. A person cannot be the father of himself, so therefore for X belonging to the relation set A, X comma X do not belong to the relation R, since a person cannot be itself's father. Therefore R is not reflexive. Now we'll quickly check for symmetric next. For X comma Y belonging to the set A, we'll just assume if X comma Y belongs to the relation R. This implies that X is the father of Y. Now here, if X is the father of Y, then this is going to be the son. Now the other way around is not true, because Y is the son, Y cannot be the father. This implies that Y is not the father of X. This implies that Y comma X do not belong to the relation R, therefore R is not symmetric. Lastly, we'll check for transitive behavior. Now you're given for X comma Y comma Z belonging to the set A, will assume X comma Y belonging to this relation R. Now this implies that X is the father of Y. Now next we'll assume that Y comma Z belongs to the relation R. This assume that Y is the father of Z. That means we have X here. he is the father of Y, right? Now Y is the father of Z, so in the relation X is going to be the grandfather. So we can say that therefore X is not the father of Z, therefore X comma Z do not belong to the relation, therefore R is not transitive. Therefore if you've seen here, therefore R is neither reflexive nor symmetric and nor transitive. So that's it for this video. I'll see you next in the next one. We'll carry on with the second question. Thank you so much. Do subscribe to our channel Bright Minds Academy Goa.